Welcome to section 4.6, day 2, solving related rates problems. Today's objective is to solve related rates problems utilizing similar triangles when necessary. I'll also use this for when we're doing similar figures. So our strategy: draw a picture and identify the information we know or want. Write an equation relating the variable whose rate of change we want to the variables whose rate of change we know. Differentiate both sides of the equation implicitly with respect to time. And then, after you differentiate, substitute any known values and solve for the rate that we want. We're going to go through a couple of these so you can see what I mean by this. There's our 4-step strategy. So the area of a perfectly round puddle, yes, it's perfectly round, is increasing at a rate of 81 pi squared inches per hour. How fast is the puddle's radius increasing? At the instant, the radius is 12. Well, we know a couple of different things. We do know our formula for the area of a circle, which is pi r squared. And we also know this, which is our radius is changing, our rate of change, dA dt, is 81 pi inches squared an hour. So that is what we know. We also know we want to do this when the radius is 12. So on this equation, we only have two variables. So all we have to do is take the derivative of the area function. And we do that implicitly with respect to time. So dA dt is 2 pi r dr dt. We have differentiated. We can now plug in what we know. We know that dA dt is 81 pi, and I'm going to put these in for measurements, inches squared an hour. And we know that equals 2 pi times 12 dr dt. And then we're going to solve for dr dt. And when you have 2 pi times 12, you get 24 pi. We're going to divide both sides by 24 pi. And when we do this, we will get 3.37. And you divide inches squared an hour by inches, 12 inches, we are going to get inches an hour. This is dr dt. So what this is saying is if my puddle's size is increasing at 81 pi inches squared an hour, and our radius is at 12, then the radius is changing 3.375 inches per hour at that time. And this is a simple related rates problem. We wrote our formulas, we identified what we knew, we then differentiated. After we differentiated with respect to time, we plugged in the values that we knew, and we solved for, in this case, dr dt, what we were looking for, the instantaneous rate of change of the radius. We also have what we call related rates with similar triangles. We can use this also with similar figures. We're going to be working with similar triangles. We solve using the same strategy. We draw pictures, we define variables, we write equations, and then we do implicit differentiation. And you'll see we have the volume of a cone is 1/3 pi r squared h. We will need that on our next slide. One thing that's different with this one is the last problem we only had two variables. This problem we are going to have three. We have volume, we have radius, and we have height. So with these problems, we often have to write one of the variables, well, we almost always have to write one of the variables in terms of the other. So we solve for the variable that in terms of the other using similar triangles. Let's see how this looks like. Water is running into a conical tank at a rate of 9 feet cubed per minute. The tank stands point down and has a height of 10 feet and a base radius of 3 feet. How fast is the water level rising when the water is 6 feet deep? You'll notice I already have a picture here. I have my radius of 3, we have a height of 10, and then my height of my water is h and r, because we don't know what those values are. So first thing I'm going to do is write down what I know. So what do I know? I know the volume is changing. We know dV dt is 9 feet cubed a minute. We also know that the height is 10 of our conical tank and that my radius is 3. We also know that we're going to try to find this when h is 6. So how fast when h is 6? That is what we're looking for. So we want to find, in step 2, we want to find out how fast the height is changing. So we want to find dH dt is what we're looking for. And we don't care about the radius. So we don't want, and we don't know anything about dr dt. So this will help us, because what that means is that when we set up our function, we want to remove our r's from our function by having them in terms of h, our height. Because all we want to have in this problem, since remember our formula is volume is 1/3 pi r squared h. So remember from this, we have 3 variables in here. Well, we know dV dt. We know we're working with height. So we're going to write r in terms of h. So we are down to 2 variables. All right, so step 3, we are going to write r in terms of h. And we're going to use these similar triangles because they're proportions. We can say the radius over 3, the smaller over the larger, is the same for our height, the smaller over the larger. And we can solve for r, and r is 3h over 10. So now we have written r in terms of h. So when we plug stuff in, we won't have to worry about the r variable. We will be able to plug it in and change it so there's h variables. So the 4th step, we are now going to differentiate our function. First, we're going to plug in r as 3h over 10. So now we have volume is 1/3 pi. Our r is now 3h over 10 squared, and then times h. We're going to simplify this down. So we're going to multiply. We're going to take the square of 3h over 10, which is 9h squared over 100. Actually, I'll write this out. We have 9h squared over 100 times h. And when we simplify this whole thing, we get that the volume is 3 pi h cubed over 100. So this is what I'm going to take the derivative of. So we have 3 pi h cubed over 100. We then take the derivative of the volume function, and we get dV dt equals 9 pi h squared over 100 dH dt. We are now going to plug in the stuff we know. We know dV dt is 9, because it's 9 feet cubed a minute. We know we're looking at this when our height is 6. So 6 squared over 100. And we do not know dH dt. That's what we're trying to solve for. How fast is dH dt changing, the height changing? Okay, so we're going to solve this. And when you do this, you end up getting 900. You take 36 times 9 times pi. You're going to divide that on both sides, and you get 324 pi. And this is my dH dt. You use your calculator if you're allowed to use a calculator on this type problem, and you'll find that this is 0.884, and we're changing our height, feet per minute. This is my dH/dt. So the height is changing at 0.88 feet per minute when the volume is changing at 9 cubic feet per minute. This is a common style of related rates problem. So you write down what you know, you find out what variable you don't really, I shouldn't say care about, but one that you don't need, so you can write that variable in terms of another variable in your problem. In this case, we didn't have any information about radius. We didn't want to find the radius, the change in radius, so we rewrote radius in terms of height using similar triangles. Make sure when you do these that you do label it with the proper measurements. In this case, we have feet per minute because we're talking about the height. And that is all. Solving related rates problems with similar figures. Thank you for watching and have a nice day.